Hi everyone, this is video number 6 of our complex number lecture, P3 chapter 10, and on the screen right now is page 16 of P3 chapter 10 notes. Okay. In this video, we are going to study the geometrical meaning of some common expressions involving modulus and argument. Okay, so we are going to interpret what does modulus and argument mean in an Argand diagram. Right? Okay, so let's read through the first paragraph here. Okay, so why do we need to study the geometrical meaning of modulus and argument? Because later on in topic 10.2 locus, which will start from page 26. Right? So in the section of locus, understanding about the geometrical meaning of modulus and argument will help us a lot. Right, so this page 16 here is actually to prepare you better for topic 10.2 on locus. Okay, so this paragraph says let U and V be two complex numbers where x1, y1, x2, y2 are all real numbers. Okay, then the point representations of the two complex numbers U and V can be denoted by capital U and capital V respectively, with coordinates x1, y1 and x2, y2 of course. And when we talk about the vector representations of U and V, then the vectors will be OU and OV. Okay, for illustration purpose, I'm going to use some numerical example here. Okay, so for illustration purpose, I will let U to be a numerical complex number. Let's make it 2 plus 3i, and I'll make V to be -1 plus 4i. Okay. Then if I depict these two complex number on an Argand diagram, I'll try to draw this diagram to scale so that you can easily see what's happening diagrammatically. Imaginary axis and the real axis. 2 plus 3i will be the coordinate 2, 3. Okay, so I can denote this point by capital letter U. So this capital letter U will be the point representation of the complex number 2 plus 3i. And -1 plus 4i, it will be -1, 4. Okay, so this coordinate, I'm going to label it as capital V to represent the complex number V. Okay. And now let's study the three tables at the bottom of page 16. Okay. So table number 1 tells us the correspondence between complex numbers and vectors. Okay. So we know that the vector representation of the complex number U will be the vector that connects the origin to the point U. Okay, so I'm looking at the first row of this table. So the complex number U, the vector representation will be the vector directed from the origin towards the point representation of the number U, which is the capital letter U there. So OU is a vector representation of the complex number U. And yeah, I also describe this vector OU in words. It is a vector directed from origin to U. Okay. Then similarly, the vector OV is a vector representation of the complex number V. You just need to direct a vector from the origin towards capital V. Okay, so the red and the green arrows, they are vector representations of the complex numbers U and V respectively. Okay. Now, when we take the difference of two complex numbers, when we take V minus U, we can also visualize V minus U as one single vector on the Argand diagram. Okay. So, if we take the complex number V minus U, the vector representation, because OU represents the complex number U and vector OV represents the complex number V, So V minus U, it is naturally OV minus OU. It works this way. Because OV represents V, OU represents U. So V minus U is just vector OV minus vector OU. In the chapter of vector, we know that in general, if you have the vector AB, you can write as OB minus OA. It's always O to the endpoint minus O to the starting point. And similarly, UV is the same as OV minus OU. It's still O to the endpoint minus O to the starting point. And so OV minus OU, it can be equated with UV. So this means that the single vector UV is the vector that represents the complex number V minus U. And now let me just draw out the UV here from U to V. Now if I draw out the grid boxes, it will be clear to you that the vector UV is actually 3 units to the left and 1 unit up. The vector UV, according to our Argand diagram, it is 3 units to the left. That means -3 as my x component and +1 as my y component. Okay, so from this vector of -3, 1, we can tell that the complex number represented by the vector UV would be -3 plus 1i, or simply -3 plus I. This will be the complex number represented by the vector UV. Now, if we do the traditional subtraction of V minus U, which is the -1 plus 4i minus 2 plus 3i, when you do your computation, you are going to get -1 minus 2 as the real term, that is -3, and the +4 minus 3 as the coefficient of I, that will be a +1i. So now observe that this thing that we have here is consistent with what we had on the right of your screen. We know -3 plus 1i is a complex number represented by UV. And -3 plus 1i happen to be the same as V minus U. So that means that the complex number represented by the vector UV, it must be V minus U. It must be V minus U. Okay, so we have one simple way to remember this fact. Okay. So what is vector UV? It is a vector directed from U to V. And so that means that whenever you have the complex number V minus U, the complex number that comes after the minus sign, the complex number that comes after the minus sign is point representation. It becomes the starting point of your vector. Starting point of the vector representation. Okay. The complex number that is being subtracted. Okay, this is complex number that is being subtracted. Its point representation is going to become the starting point of the vector. So if you have V minus U, then your vector should start from U and directed to V. Similarly, the single complex number U that we had in the first row of this table, U can be interpreted as U minus 0, right? U is equal to U minus 0. And so if you treat U as U minus 0, that tells you that the point representation of 0, which is the origin, it becomes the starting point of your vector representation. Okay? Origin becomes the starting point of the vector representation, which is correct because the vector representation is OU, where the starting point is O. And similarly, V, because it's V minus 0, V is the same as V minus 0. So again, the point representation of the number 0 becomes the starting point of your vector. And the ending point of your vector will be the complex number that is before the minus sign. Okay. So for the case of U minus 0, it is a vector from O to U. V minus 0 is a vector from O to V. v minus u is vector from u to v, and u minus v, the last row here, because v comes after the minus, so point v becomes the starting point of your vector representation. Right, so it's useful to remember this. When you have a subtraction of two complex numbers, the number that is being subtracted becomes the starting point of your vector, while the number that is before the minus sign, its point representation is the ending point of your vector. V minus u means vector uv, u minus v means vector vu. Okay, now let's go on to table number 2. Geometrical interpretation of expressions involving modulus. Now, earlier in this chapter, we have learned that the modulus of a complex number, for example, modulus of 3 plus 4i, it is actually the length or the distance from the origin 0, 0 to the point representation of 3 plus 4i, which is 3, 4. The modulus of a complex number is the distance from origin to the point representation of that complex number. So, referring to our u and v in our discussion here, the modulus of u is just length of the vector OU, which is the length of my red colored vector in the diagram. Okay, so if we calculate it using the formula for modulus that we have already learned, the modulus of u, according to our example, is the modulus of 2 plus 3i. Okay, and if you take the formula of square root x squared plus y squared, that will be square root of 2 squared plus 3 squared, and that is surd of 13. If you really try to calculate the length of your red colored vector in the diagram by Pythagoras theorem, you would also get surd 13. It will be consistent. Okay, so you can look at this right angle triangle here, where your horizontal side has a length of 2, your vertical side has a length of 3, and by Pythagoras, you can get the length of the vector OU as square root of 2 squared. Square root of 2 squared plus 3 squared, which is also surd 13. And similarly, the length of your vector OV, which is the length of the green color vector, if you calculate the modulus of V using the formula that we have learned earlier, it will be modulus of minus 1 plus 4i, which is square root of minus 1 squared plus 4 squared, and you will get a square root 17. So again, if you use your diagram, using a right angle triangle and treating OV as the hypotenuse of this right angle triangle, then you will be able to get the same length of square root 17 as the length of OV. Okay, because your vertical side have 4 units of length, your horizontal side has 1 unit of length, so square root of 4 squared plus 1 squared gives the length of the hypotenuse OV. Okay. Okay, so far nothing special about modulus of u and modulus of v, because it's the same as what we have learned earlier. Okay. Now the thing that is new here that I want to introduce to you is when you have modulus of a difference of two complex numbers, modulus of v minus u. So what does it mean then? Okay. So modulus of v minus u, earlier in table number 1, we have learned that v minus u has the vector representation of uv. Okay, so modulus of v minus u, since we know the vector representation of v minus u is a vector uv, is a single vector uv. So when we take modulus of v minus u, it is just length of the vector uv. It is just length of the vector uv. That means that when the Argand diagram is already available, when the Argand diagram is already available, you can easily use your Argand diagram to find the length of the vector uv and just take it as the value of the modulus of v minus u. Okay, so let's look at our Argand diagram that we have there. Okay, so if you use the Argand diagram to find length of vector UV, or simply modulus UV with an arrow above. Okay, this is the notation for length of vector UV. Okay, so according to Pythagoras, I will have 3 squared plus 1 squared, and that gives me a square root of 10. Okay, so this square root of 10 can be taken straight away as the modulus of the complex number uh, v minus u. We write v minus u because remember that the complex number that comes after the minus sign, it becomes the starting point of the vector. And the number that comes before the minus sign, it is the ending point of the vector representation. So this gives you a convenient way to calculate modulus of a subtraction between two complex numbers. Also, remember that earlier on page 15, we learned about properties of modulus and argument. And if you look at the left-hand side of this table here, there is no property of modulus that tells us how to deal with modulus of v minus u. So don't create your own property here. The modulus of v minus u in general is not the same as modulus v minus modulus u. So don't simply distribute your modulus over the negative. It doesn't work that way. It doesn't work that way. Okay. Right. Okay. Just to convince you that our geometrical interpretation of modulus v minus u is actually correct, I will just try to calculate the modulus of v minus u using the traditional calculation that is on the left of your screen. V minus u, earlier we have computed it to be minus 3 plus I. Therefore, modulus of v minus u is just modulus of minus 3 plus I. Then if you use the formula to calculate modulus, which is the square root of x squared plus y squared, you again get square root of 10. Right? So the square root of 10 that we obtained just now at the top right corner of your screen by referring to the Argand diagram is actually correct. Right? So this is one important thing that you need to learn here. When you have modulus of v minus u, it is just length of the vector uv. It's just length of the vector uv. Or simply distance from u to v. A distance measured from u to v. And similarly, for u minus v, we know its vector representation is a vector starting from v. This becomes the starting point, starting from v and ending at u. So you have vector vu here. So modulus of u minus v is just length of the vector vu, or simply the distance measured from v to u. So here, of course, distance from u to v and distance from v to u must be the same distance because they are connecting the two same points. Vector uv and vector vu are different, but these two vectors will have the same length. Now, similarly, the modulus u itself, it can be interpreted as modulus of u minus 0. And when we have subtraction of two complex numbers here, 0 itself can be treated as a complex number 0 plus 0i. So u minus 0, it can be treated as a subtraction of two complex numbers. Right. So this 0 here will become the starting point of the vector representation, while the u here becomes the ending point of the vector representation. Since u minus 0 is vector is OU, so modulus of u minus 0, it makes sense to treat it as length of the vector OU, or simply distance from origin to u. Then here, because modulus v can be treated as modulus of v minus 0, and therefore it can be taken as length measured from origin to v. So when you have a subtraction between two vectors, always remember that the number that comes after the negative becomes the starting point of your vector. Okay. Right, now let's study the third table involving argument. Let me just copy down this Argand diagram so that I don't have to keep scrolling up and down. I just paste it down here. Okay. Now, argument U, okay, in page 13, we have learned how to measure the argument from a diagram. Right, so the argument is always the angle measured from the positive horizontal axis, or in other words, from the right-hand side direction, towards the slanted vector. And that slanted vector will be the vector representation of that complex number Z. Okay, so in this case, argument of U, it will be the angle measured from the positive x direction towards the vector representation of the complex number U, which is this angle that I'm labeling as theta on the diagram there. Right, so this theta here will give me the argument of U. Okay, so it tells us the direction of the vector OU as measured from the horizontal, the positive x direction. Right, so argument of U, it tells us the direction of the vector representation of U, which is a vector OU, as measured from the positive x direction. So informally, this second geometrical interpretation, this one is actually very useful, especially when we learn the topic of locus. Right? Right, so informally, I like to call it angle measured from origin to U. I like to call it angle measured from origin to U. I said this description here is informal because the complete description is actually the angle measured from the direction of the positive real axis, to the direction of vector OU. Yeah, the formal description or the complete description is actually this sentence that I'm writing in blue color. But in short, it's easier to just informally call it angle measured from origin to U. And so when I informally say angle measured from origin to U, what I mean is you will draw a horizontal line starting from origin. Starting from origin, you will draw a horizontal line towards the right, and it is along that green dotted line that you will measure the angle theta towards the slanted vector OU. And so angle measured from origin to U, it will be measured from a horizontal line starting from the point at the origin, and you measure the angle towards a slanted vector that connects origin to U. So that's what I mean informally by angle measured from origin to U. And similarly, argument of V, in the diagram we know, argument of V, it will be this purple color angle alpha here, where I start from the positive real axis and I measure the angle towards the slanted direction OV. Okay. Why am I using the vector OV? Is because OV is a vector representation of the complex number V. Okay. So informally, I call this angle alpha as an angle measured from origin to V because it is from the origin that I draw a horizontal line towards the right, from which I measure the angle. Okay. Now, what's more important or what's new here is when we have a subtraction between two complex numbers in the argument expression, how can we interpret it diagrammatically? When you have argument of V minus U, first of all, argument cannot be distributed over negative. argument of v minus u is not the same as argument v minus argument u. There is no such property. There's no such property. You can refer to page 15. There is no such property. So don't simply distribute the argument over a minus set. Okay. Now, earlier in table number 1 on page 16, we have learned that v minus u is vector representation, is the vector that starts from u and ends at v. The number that comes after the minus, it becomes the starting point of your vector, right? While v becomes the ending point. So it's a vector u to v. Okay. So diagrammatically, its interpretation is very easy. So since argument of v minus u, it should tell us the direction of the vector uv. It is simply just angle measured from u to v. It's simply angle measured from u to v, which means in the diagram, you can just draw a horizontal line towards the right, starting from the point u. Starting from the point u, you draw a horizontal direction towards the right. And then from this direction of your green dotted line, you will measure the angle towards the vector uv. Suppose that this angle is beta, and then this beta will be the argument of v minus u. As simple as that. Now, to those who find this thing hard to accept, now I will try to convince you that this actually works and is correct. Okay. So earlier we have learned that, not learned, but earlier we have computed that v minus u, according to our illustration and the numerical example here, that v minus u is negative 3 plus I. So I'll take this information down. And just to convince you that the geometrical interpretation is actually correct. Okay. Now, then the argument of v minus u, it will be the argument of minus 3 plus I. Right, so if we use the method that we learned earlier on page 14 to find this argument, right, then the way we'll find it is we'll first figure out in which quadrant does the point representation of negative 3 plus I lie in. Okay, that will be minus 3 here and 1 here. Okay, this will be the point representation of minus 3 plus I. Okay, then we'll draw a vector from the origin towards this point representation, and we'll measure the angle from the positive x direction towards the slanted vector. Okay, so according to the method we learned on page 14, we can take 180 degrees and then reverse by the basic angle. Okay, so that will be pi minus inverse tangent of modulus y over x, okay, where y is a coefficient of I and x is a real term. Okay, so you have pi minus inverse tangent of 1/3. Okay, I just compute it using my calculator. Pi minus inverse tangent of 1/3. Remember to switch your calculator to radian mode, and you get a 2.82 to 3 SF. Okay. Right, so 2.82 is the argument of v minus u. Okay. Now, is it the same as the beta there on your diagram? Okay, so according to table 3 on page 16, it tells us that argument of v minus u is simply the angle measured from u to v, which is labeled as beta on my diagram. Now, using my diagram, let's try to find this angle beta. Okay. Before that, I will make use of this right angle triangle that I'm coloring in dark blue here. And I'll call this very small angle as gamma. Okay. The small angle then that I'm coloring in dark blue, I will call it gamma. Okay. So on this right angle triangle, the vertical side will have a length of 1. The horizontal side will have a length of 3. Okay, so I can find tangent of gamma as opposite over adjacent, which is 1 over 3. And that means my gamma must be inverse tangent of 1/3. and I only take the acute answer. But when I write inverse tangent of 1/3, the answer must only be acute. Anyway, right? I'll take 0.32175. Okay. Then I know beta plus gamma must be 180 degrees or pi. Okay. I know beta plus gamma must be pi. That means beta must be pi minus gamma, which is pi minus 0.32175. If you press your calculator, that gives you the same 2.82. Right, so I hope now you are convinced that the geometrical interpretation given in table number 3 on page 16 is actually correct. Because whether you calculate argument of V minus U the traditional way, or you just use your Argand diagram straight away, both methods will give you the same answer. So uh, that means we are now convinced that the method of using the Argand diagram that we used just now was actually correct. Okay. So this geometrical interpretation of argument of a subtraction between two complex numbers is very important in understanding of the locus topic later in this chapter. Similarly, u minus v, we know the vector representation is a vector that starts from v and ends at u. So it's the vector vu. And so argument of u minus v is the direction of the vector vu, which is simply the angle measured from v to u. Because it's a vector vu that starts from v and ends at u, so we say it's an angle measured from v to u. Informally, we say angle measured from v to u. So that also means that if you really want to find argument of u minus v from your Argand diagram, you just need to draw a horizontal line towards the right, starting from v, starting from the point v, and from that orange dotted line, you will measure the angle towards the vector vu, towards the vector vu. And so this, according to this diagram, you should expect to get a very small negative angle. Because we are measuring the angle in the clockwise direction, therefore it's a negative angle. Okay. So that concludes page number 16. Now let's move on to page number 17. Yeah, page number 16 is very important. When later we learn the locus chapter, when we learn the locus topic later, we'll have to occasionally come back to page number 16. Okay, now I will move on to page number 17. Okay, page number 17 is solving Argand diagram problems using vector representation of complex numbers. Point number 1 says there are certain Argand diagram problems that appear to be solvable using coordinate geometry, but when you try to solve the problem using coordinate geometry, you find the calculations too tedious. Okay, so one example of such kind of question will be your homework question, the very last question. Okay, I'll just switch to the very last page. Okay, question 18 of your homework. Okay, so this question, it gives you complex numbers u and v, given by u equals 1 plus 2 to 3i and v equals 3 plus 2i. And they say in the Argand diagram, the point representations are a and b, respectively. A third point C lies in the first quadrant and is such that BC equals to AB, angle ABC equals 90. Okay, so you can try to draw out your Argand diagram. And then the first idea that comes to mind to most people might be to solve it by coordinate geometry. And now I will just show you the homework solution that I've already uploaded onto Google Drive. Right, this one. So when you visualize the Argand diagram, it will look like this. Okay? And they give you a 90 degrees here. Okay? And they say BC is twice the length of AB. Okay? So BC is double the length of AB. Okay. Yeah. So okay. So when you look at this diagram, the first idea that comes to mind may be I can let the coordinate of point C be xy. Okay, then I can make use of this 90 degrees where I know my gradient of AB times with my gradient of BC will give me -1. And then from here, I will get some equation involving x and y. Okay, equation in x and y. Okay, and then I can also make use of the fact that BC has twice the length of AB. Okay, so I can calculate the length of BC and equate it with 2AB. Length of BC will have this square root of x minus 3 squared, y minus 2 squared. And it's 2 times square root of uh, 1 minus 3 squared plus with 2 sub 3 minus 2 squared. And then from here, you will get another equation in x and y. And then since you have two equations and two unknowns x and y, it should be possible to solve for the unknowns x and y. Okay, however, the computation will be quite tedious. The computation is unfortunately quite tedious because your x and y would have a power 2 upon expansion of this quadratic. And also, the numbers will be quite messy due to the presence of a square root over here. Due to the presence of square root over here, the numbers will also be a bit messy. Right, so and you will notice that the computations will be much less tedious if you do it using the vector representation approach. Okay. Right. Now I'll just show you very quickly. Yeah, so if you do it by vector representation, you will notice that the computation that I do at the end is rather short. Yeah. And so the computation I do is actually only here. And it's comparatively easier as compared to if you do it using coordinate geometry. Right. So that's why I would want to introduce you to the vector representation approach to do certain questions. Okay. So let's go back to page 17 of your notes. Okay. Okay, so here it says when you try to solve an Argand diagram problem using coordinate geometry, sometimes you find the calculation too tedious. In such a case, you may consider using the vector approach. Okay, so it's not a must to switch to vector approach, but if you want to avoid the tedious computation under coordinate geometry method, then you can consider the vector approach as an alternative method. Point number 2 says, if there is a right angle involved in the problem, the following information may be useful when solving using the vector approach. So, especially when there is a right angle involved, solving using the vector approach is quite convenient, I would say. So, you need to know about this fact. Multiplying by I is equivalent to an anti-clockwise rotation of the vector by pi over 2 radian. Now, to convince you that this is true, so suppose that we have a complex number z. Let z be a complex number. Where the modulus of z, I just call it r, and the argument of z, I call it theta. Then I want to study what happens to the modulus and argument when I multiply z by I. So in other words, we want to find out what is the modulus of zi and what is the argument of Zi? We want to find out. So if you are able to find this out in terms of R and theta, then we can figure out what happens when we multiply any complex number by I. Because here I'm setting Z to be a general complex number. This Z can be any complex number. Right. So let's do some computation here. Modulus of Zi, by the property of modulus on page 15, we learned that modulus can be distributed over multiplication. Therefore, we can write as modulus Z modulus I. Modulus of Z, here we set it as R. Here we set it as R. But what is modulus of I? So modulus of I, according to the traditional method that we learn on page 14, we just need to find out what is the point representation of the number I on the Argand diagram. To find the number I, which is the same as 0 plus 1I, its coordinate on the Argand diagram will be 0, 1. It will be 0, 1. So its modulus will be the length of the vector that connects the origin to the point 0, 1, which obviously is just 1 unit. The length is obviously 1 unit. So therefore, modulus Z times modulus I is just R times 1. Because modulus I is exactly 1. And that means R times 1 is R. So what can we deduce from here? The modulus of Z is R. The modulus of Zi is also R. That means the length of the vector representation remains unchanged. Length of vector representation of Z remains unchanged when Z is multiplied by I. Because after multiplying by I, and we find the length of the vector representation of Zi, it is still the same R. Or maybe to make it less confusing, length of vector representation of Z is the same as length of vector representation of Zi. Yeah, this sentence is less confusing. Okay. Okay, then what happens to the direction of the vector representation? Okay. Let's study what happens to argument Zi. The argument, if you recall on page 15, it has a similar property to logarithm that allows you to write as argument Z plus argument I. The argument Z at the beginning in red color, we introduce argument Z to be theta. So I just write theta here. Argument of I is the angle measured from the positive x direction. Refer to the Argand diagram on the right of your screen. You start measuring from the positive x direction towards the vector representation of the number I, which in this case is 90 degrees or pi over 2 radians in the positive direction. So we'll add by pi over 2. Because from the Argand diagram, we know that argument of I is pi over 2 radians. Now, but what is theta here? Theta is the same. So let's make some comparisons here. Argument of Z is theta. Argument of Zi is theta plus pi over 2. So that means that when we multiply the complex number Z by an I, the argument gets increased by pi over 2. The argument gets increased by pi over 2 when we multiply the complex number Z by an I. So in other words, we can write argument of Zi is the argument of Z plus pi over 2. Because theta is the same as argument of z. So that means that the direction of vector representation of zi is the same as direction of vector representation of z plus by pi over 2. Okay. And so what can we conclude from here? Okay, we know that earlier the modulus of zi is r, therefore we deduce that the length of the vector would remain unchanged when you multiply the complex number by I. And then when we study about the argument, we know that the argument gets added by pi over 2. So that means for whatever complex number z, okay, so I just draw a random complex number here, maybe somewhere in quadrant 4. Okay. Suppose that this is z. Okay. And suppose that the vector representation of it has the length of, let's say, 3 units. Now, to get the vector representation of z times I, even though I do not know what z is, as long as this angle theta is known, okay, then I just need to measure the same theta here. Okay, draw a line here that makes a 90 degrees with my purple line, okay, and measure 3 units along the dotted line. Okay, I measure 3 units. The ending point of my red color vector, it will be the point representation of zi. And here you observe that the length from O to Z and the length from O to Zi are the same. And also, the argument of Zi is actually the argument of Z added by 90 degrees. Okay, because we are rotating, this is rotate by pi over 2 radians anti-clockwise. Okay, so rotation by pi over 2 anti-clockwise means the argument gets increased by pi over 2. Yeah, so okay, so from here we have to remember this fact given in point 2a. Okay, so multiplying a complex number by I is equivalent to rotating the vector representation of the original complex number by pi over 2 radians anti-clockwise. Multiplying by I is equivalent to anti-clockwise rotation by pi over 2 radians. And later, when we do some questions on page 18 and 19, you'll be able to understand better. Okay. Now, let's study also point 2b. Multiplying by negative I is equivalent to an anti-clockwise rotation of the vector representation by pi over 2 radians. And the way we explain this will be similar to point 2a just now. Okay, so if we let z be a complex number, okay, where modulus z is r and argument z is theta, okay, then we're going to study what happens when z is multiplied by negative I. Okay, we're going to study what happens to the modulus and argument. Okay, so the modulus of z times negative I, it will be modulus of z times modulus of negative I. Okay, but we know modulus of z is r. Modulus of negative I is minus pi over 2. Okay, you can always use the traditional method. We visualize the Argand diagram, and you know negative I is just 0 minus 1i. So your point is 0 minus 1. Okay, this is a point representation of the number negative I. Okay, and its vector representation is this way. So you measure a 90 degrees in the negative direction. Okay, that's why you have a negative pi over 2 as the, okay, sorry, modulus is the length, not the angle. Okay, modulus is the length. Sorry for the mistake. As a modulus of negative I, it will be the length of this vector representation. It will be this 1 unit. This is 1 unit, yeah. So you end up having an arc. Right? So again, we realize that the modulus of z is the same as modulus of z times minus I. Right? That means the length of the vector representation of z would remain unchanged after you multiply z by negative I. Okay, then if we study the argument of z times minus I, it is the same as argument z plus with argument of minus I. Okay, so referring to the top right corner diagram, to find the argument of negative I, you just need to measure an angle starting from the positive x direction towards the red colored vector, and that is negative angle of pi over 2. Okay, so you have argument z is theta, and this is plus negative pi over 2. That means you have theta minus pi over 2. Okay, so this shows us that when we multiply the complex number z by negative I, the argument, which is originally theta for the z, it becomes reduced by pi over 2. It becomes reduced by pi over 2. Or in other words, the vector's direction, it gets rotated in the clockwise direction by 90 degrees. At the same time, the length remains the same, because earlier we had that result that the modulus of z is the same as modulus of z times minus I. Okay, so this also means that okay, for any random complex number z, for example, I have this complex number here. Let's say with a length of 3 units from the origin. Okay, so if I know this theta here, I just need to measure the same theta here, and it will be a 90 degrees here. Yeah, because this angle would then be 90 degrees minus theta. And if I measure the blue colored length to be also 3 units, then the ending point of my blue line, that will be the complex number of z. That will be the point representation of z by minus I, or simply negative iz. Okay. Now, that being said, I want to add some remark here. I will give you one numerical example just to convince you that it works. Okay, so for example, I take this z to be negative 2 plus I. Okay. And let's say I try to find argument of z using the traditional way. Okay, so I have minus 2 and 1. I have this slanted vector here. So I should take pi reversed by the basic angle. And so pi minus inverse tangent of modulus y over x. Yes, pi minus inverse tangent of 1/2. Pi minus inverse tangent of 1/2, that is 2.6779 radians. Okay. Now, the argument of when the argument of zi, when the argument of zi, or in other words, when the vector is rotated in the positive direction by 90 degrees, if this is z, then if you're asked to find zi, then I mean, what would be the argument then? What would be the argument here? So if you want to use the properties of argument z plus argument I, you can use it. And you know argument z is 2.6779, argument I is pi over 2. And so if you press the calculator plus pi over 2, you will get 4.2487 radians. But however, this is no longer in the principal range. No longer in principal range. Yeah, because recall that the principal range for an argument is from negative pi to pi. Hey, but 4.24 is already more than pi. It's already beyond pi. Okay, so typically, if there is no other special instructions, by default, we are going to write our answer for arguments uh, within the principal range. And so what we'll do here is we're going to reduce this angle by one cycle. By one cycle, I mean 2 pi. We're going to reduce this angle by one cycle so that we end up with an answer in the principal range, and it remains to be the same direction. We are going to reduce it by one cycle. So here, it will be a bit problematic if we write equal here, because 4.2487 is not the same as 4.2487 minus 2 pi. They are numerically not the same. And so to fix this issue, I will just use a triple horizontal line here. And so here, the triple horizontal line doesn't mean an identity, it means equivalent. So in this context, the triple horizontal line can mean equivalent. And then that fixes the problem that 4.2487 and 4.2487 minus 2 pi are actually numerically not equal. But they are equivalent in the sense that they point towards the same direction. So if you press a calculator, you will get negative 2.03 to 3SF. And then this negative 2.03 is within the principal range. And if you really check the Argand diagram that you have there, negative 2.03 radians is actually an angle in quadrant 3. It's actually an angle in quadrant 3 because the downward direction will give you negative pi over 2 radian, which is negative 1.57 roughly. So negative 2.03 will be even more negative, and that means it must be in quadrant 3. And just to convince you that our Argand diagram that we obtained by rotating by 90 degrees is actually correct, let me just calculate Zi using the traditional way. Zi will be minus 2 plus I times I. That is minus 2I plus I squared. I squared is negative 1, so that is minus 2I minus 1. I rewrite as minus 1 minus 2I. Okay, so the point representation should be negative 1, negative 2. And so if you look at the quadrant 3 then, it makes sense for this point to be in quadrant 3 because both the x and y coordinates are negative. Right. Now let's move to page number 18. And we'll solve this question using the vector approach. And just to familiarize you with this approach. Okay, so notice that this question actually didn't tell us what approach to use. You can use the coordinate geometry approach if you don't mind the tedious calculation. Okay, but for me, I would prefer to use the vector approach. Okay, ABCD is a square with the letters in anti-clockwise order. The points A and B represents 2 plus 3i and 6 plus I respectively. Okay, so point A would have coordinate 2, 3. Point B will have coordinate 6, 1. Okay, now let's draw out the Argand diagram. They don't really ask for a diagram, but it helps to have a diagram to visualize what's happening. Okay, let me just draw out this diagram and plot the points A and B. A is 2, 3. B is 6, 1. 6, 1 should be down here. Okay, here's my point B. Okay, so ABCD forms a square with the letters ABCD in anti-clockwise order. Okay, so if AB goes this way, this is an anti-clockwise direction. Okay, so it should go up this way. Okay, so you should expect your C to be roughly here. Okay, at this stage, I'm still not sure where the exact coordinate of C is, but I know it should be at the top right direction from B. I expect my C to be roughly here. I expect my D to be roughly here. At this stage, I'm still not sure. Yeah, but anyway, at least now we roughly know where C and D is located with respect to A and B. Okay. Okay, find the complex numbers represented by C and D. The question wants us to find. Okay. That means once we are able to find out the coordinates of C and D, we will be able to get the complex numbers represented by C and D. However, the problem here is the information that we have is not too much. We only have point A and point B, and we can use point A and point B to find the length of AB and also the gradient of AB. That's all that we have. It's going to be a bit painful to find C and D using the traditional approach because you have XC, YC, unknown coordinates for C, XD, YD, unknown coordinates for D. So there are actually 4 numbers that we have to find. 1, 2, 3, 4. There are 4 numbers that we have to find. Solving for 4 unknowns will be quite a pain. It will be quite a pain. It's possible to do, but it will be quite a pain. Some people may be thinking about using the center of this square, knowing that BD and AC share a common midpoint here. Yes, you can also use that to form some equations. But still, solving for 4 unknowns, XC, YC, XD, YD, is quite a pain to do. Right? So let's try to use the vector approach here. You will find the vector approach to be much more easier in terms of the computations involved. Okay. So now I will just write my working at the right of your screen. Okay, when using the vector approach, I will encourage you to construct a table where your first column you write down the vector representation. And the next column, you write the complex number that is represented by the vector. Okay. I will let small letter A to be 2 plus 3i. I let small letter B to denote 6 plus I, just for convenience. Because when I construct this table, usually I don't like to do calculations in. I just want to obtain some expressions in terms of A and B. And I prefer to do calculations at the very end. Okay. So to find the complex number represented by C and D is to find the vector OC and OD. Once you have the vector OC and OD, you can just read the vector to obtain the complex number. Okay, so let's think about the idea first. How can I get the vector OC from the limited information that I have? Okay. Vector OA, I can have it very easily. Vector OA, because I have the coordinates of A, so vector OA I can easily obtain. Vector OB I can also easily obtain. Now, because ABCD is a square, I know that vector AB and vector DC must be the same vector. Vector AB must be equal to vector DC because these two vectors have the same length and the same direction. And recall from the chapter of vector, for two vectors to be equal, we need them to have the same length and same direction. Similarly, vector AD is the same as vector BC because they have same length, same direction. Okay, so we'll use this information later. Okay. So to obtain the vector OD, I can just travel from O to A, followed by A to D. I can just find OD by taking OA plus AD. Okay, I'll use this later as well. And I can also find vector AC, OC, vector OC, by taking the path O to B followed by B to C. We'll use this later. Now, with all those in mind, let's complete the table in purple color. Okay. So I'll start with the known vectors OA and OB. And so I know that vector OA represents a complex number A, vector OB represents a complex number B. Okay, I just draw a line here so that it's easier to see. Okay. Now, I can get the vector AB as OB minus OA. And this is from our knowledge in the vector chapter. And so since AB is OB minus OA, the complex number represented by AB, it will be the corresponding B minus A. Because OB represents B and OA represents A. It just follows. It works this way. Then we know that the vector DC. Okay, wait. Maybe I don't need DC here. I want to get the vector AD. I want to get the vector AD. Now, notice that there is a 90 degrees. There is a 90 degrees at the vertex A of the square. And so, since now I already have the vector AB, I just need to rotate. I just need to rotate this vector AB in the anti-clockwise direction by pi over 2 radian. Rotate anti-clockwise by pi over 2 radian. That will give me the vector AD straight away. And notice that AB and AD has the same length. So it's just a simple rotation. We don't have to modify the length. Right. So AB rotated to AD. Then now I know AD is represented by. Go back to the previous page, page 17. Multiplying by I is equivalent to an anti-clockwise rotation by pi over 2 radians. And so that means the complex number represented by vector AD is just I times B minus A. It's just I times B minus A. Because earlier we know that B minus A represents a vector AB. And so when you multiply B minus A by I, you would obtain the vector AD. Let me just comment at the side. This is actually rotating. Rotate vector AB by pi over 2 radians anti-clockwise. We just need to multiply it by I using what we learned on page 17. Okay. Now, AD is the same as BC. AD is the same as BC. So BC, since it is the same as AD, the complex number represented by BC, it must be the same complex number. Okay, now I think we are ready to get an expression for OC and OD. And so for OC, we can take the path OB plus BC as planned just now. OB refer to this table, the second row, you have OB represents B. BC is just IB minus A. Okay, while your OD is OA plus AD, and that OA is A, AD would be I times B minus A. Yeah, I'm just referring to the earlier rows of my table here. Okay. So now the complex number represented by C it will be just this complex number here that I'm circling in yellow, and just bring it down. Yeah, we can just conveniently bring this down because the complex number represented by the point C is the same as the complex number represented by the vector OC. Earlier in this chapter, we learned that if capital Z is a point that represents a complex number Z, then the vector OZ it must also represent the same complex number Z. Right, so here is the same logic here. The complex number represented by C, it must be the same as the complex number represented by vector OC. Right, so we just write B plus I times B minus A. Of course, we have to sub in the values of B and A that we have. B is 6 plus I. B is again 6 plus I minus A is 2 plus 3I. Okay, then let's simplify this. Yeah, expanding my I into the bracket, that's 4I minus 2I squared. I have a 5I here. I squared is -1, so minus 2I squared becomes a plus 2. That becomes 8 plus 5I at the end. Okay, and done. Then now similarly, we can find the complex number represented by D. It will be just this number, just bring it down here. Because the complex number represented by point D, it must be the same as a complex number represented by the vector OD. So it's A plus I times B minus A here. I sub in my A as 2 plus 3I. B is 6 plus I, A is 2 plus 3I. And then just expand my I into the bracket. I have a 7I in the middle here, minus 2I squared becomes a plus 2. Then that's 4 plus 7I and that. Okay, now I will move to example 4 on page 19. Oh yeah, one more thing. For your answers in example 3, make sure that the phrase complex number represented by C and also the phrase complex number represented by D is stated. Okay. Now we'll move to example 4 on page 19. Okay, example 4, I will again do it using the vector approach so that you can be familiarized with this method. So it's not a must to do this question using the vector approach. You can choose to do it using the coordinate geometry method if you don't mind the tedious calculation. Anyway, I will just do using the vector approach here. A and C are 2 points on Argand diagram representing complex numbers -5 plus 2i. So A is a point -5, 2, C is a point 1, 1. AC is a diagonal of the square ABCD. Find the complex numbers represented by points B and D. So this time the information given is slightly different as compared to the previous question. This time they give us a diagonal AC. Okay. -5 plus 2i is roughly here. No marks given for the diagram, so your diagram doesn't need to be really nice. It's just to help you to visualize what's happening. AC, C would be the point 11, which is roughly here. And AC forms a diagonal of the square. Okay. So you can expect the other diagonal to look something like this. Making a 90 degrees with the original diagonal AC. And you would expect the second vertex to be somewhere here, the third vertex to be somewhere up there. It's roughly like this. This diagram is not accurate because I do not know where my point B and D are actually, but at least it's roughly like this. Right. So whether we should assign point B to be the bottom one or the top one, it's not told by the question, so we just simply assign. So I'll simply assign B at the bottom and D at the top. You could have assigned B and D the other way around. Okay. Right. Now let's do a bit of planning first. Okay, this time we have information on the coordinates of A and C. Okay. So AC forms the diagonal, and we know the diagonal AC and BD shares a common midpoint as M. Okay. To make sure my reader knows what my M is, I will just write in sentence, let M be the common midpoint of AC and BD. Okay. Then I would also want to make use of this 90 degrees there, because knowing the coordinates of A and C allows me to form the vector AC easily. And from the vector AC, I can easily get AM and MC. I can easily get AM and MC because AM is half of AC, MC is also half of AC. Okay. So if I have the vector MC, I notice that once I rotate it by 90 degrees anti-clockwise, this is anti-clockwise rotation, anti-clockwise rotation by pi over 2 radians, and then I can get the vector MD conveniently. And if I rotate it clockwise by pi over 2 radians, I can get the vector MB easily. And then later it would be easy for me to obtain the vector OB and OD as required by the question. Okay, so let's do some calculations here. Let's construct a table as usual, and I would also introduce some symbols to denote the complex numbers so that I don't have to do so much calculations when I construct the table. Okay, I will let A be the complex number minus 5 plus 2i, and let small letter c be the complex number 1 plus I. Okay, then I construct the table as usual. The first column is vector representation, and the second column is complex number. Right. Well, maybe I should construct this table on the right of your screen so that I have more space to work there. Okay. Right. We'll start with the given information. OA complex number is A, OC complex number is C. Then I can easily form the vector AC by taking OC minus OA. So the complex number is just a corresponding C minus A. Okay. Then I would need AM or MC. In fact, you can just write both here. AM is equal to MC. Both of those, AM and MC, are equal to half of AC. And notice that AM, MC, and AC, they all point in the same direction. It's just that AC has twice the length of AM and MC. Okay, so half of AC is of course half of C minus A. It just follows. Okay, then it's time to rotate the vector. Rotate the vector MC to become the vector MD. Okay, so the complex number represented by the vector MD, it will be I times the complex number represented by MC. Okay, this MC will rotate it by 90 degrees anti-clockwise. Okay, so I have to multiply this number, half C minus A, by I. Okay, so it becomes half I times C minus A. Okay, I'm just multiplying it by I. Let me just comment here at the side. This is rotate the vector MC by pi over 2 radians anti-clockwise. So we can just easily rotate it because there is a 90 degrees there. The angle DMC is a 90 degrees, and also we know MC and MD have the same length because this is a square. Okay. Okay, so after having MD, we'll also need MB as well. And so MB can be obtained by a rotation of MC by 90 degrees clockwise. Alternatively, you can also take MB as the opposite of MD. You know MB and MD has the same length. It's just that MB has the opposite direction as compared to MD. And so MB is actually conveniently just the negative of MD. Which means it's just negative of half I C minus A. Okay. So with MD and MB available, we can now start to plan a path for OB and OD. So it would be good if we have OM. It would be good if we have OM. So let's try to find OM so that later we can just take OM plus MB and also OM plus MD to reach from O to B and from O to D respectively. Okay, so let's try to find OM there. Now to get OM, you can try to go from OA followed by AM. Right? OM is just OA followed by AM. Okay, we already have AM earlier. AM is the same as MC, so you can use this thing. And OA is just a simple A. Right? So it's A plus half C minus A. You can choose to simplify this complex number here, but I choose not to. I just leave it in that messy form, right? Because later I will do the simplification at the end. Okay, so now since OM is available, I can now plan a path from O to B. Right, so OB would be OM plus MB. The OM will be this A plus half times C minus A. MB is the negative half I bracket C minus A. Okay, and finally, I have OD to be OM plus with MD. Okay, so it's again the same A plus half C minus A, and MD is a plus half I bracket C minus A. Okay. Okay, now it's time to write down the complex number represented by B and D. Okay. Okay. Complex number represented by B. Okay, so it's just this number being brought here. And then you just sub in the numbers and calculate. Okay, what's your A? Your A, oh, okay, I write this down first. A plus half times C minus A minus half I times C minus A. Okay, just sub in all the values there and do your calculations. C is 1 plus I, A is minus 5 plus 2I. Okay, minus half I, and it's the same thing here, C minus A again. Okay, I have 6 as the real term, and plus I and minus 2I, that would be a minus I. And minus half I, this should be the same, 6 minus I. The expand again, it's a 3 here, minus half I. This is minus 3I and a plus half I squared. Okay, the plus half I squared at the end is just a negative half because I squared is negative 1. Okay, so the real terms, let's sum up. Negative 5 plus 3, negative half. That's 3 minus 5.5. That will be minus 2.5 or minus 5 over 2. Okay, then the terms containing I have a plus 2, minus 3, minus half. That gives me minus 3 over 2. Yep, minus 3 over 2. Okay, minus 3 over 2I. Okay. Yeah, next, complex number represented by D is A plus half times C minus A plus half I C minus A. And I'm just bringing down this number, which is represented by the vector OD. Just bring it down. Okay, so again, sub in your values and do your calculations. C minus A, C is 1 plus I, minus A is minus 5 plus 2I, half I followed by the same C minus A. And then just do the calculations. Okay, multiply my half, and here multiply my half I. Okay, the last term becomes a plus half because I squared is a minus 1. Okay, the real terms, minus 5 plus 3 plus half. So it's minus 5 plus 3.5. That gives me a minus 1.5, which is minus 3 over 2. Okay. Imaginary terms, I have a plus 5I minus half I, that's plus 9 over 2I. Okay, and that's it. Okay, so these are the two complex numbers represented by B and D, respectively. And so if at the beginning you have assigned B as the point at the top of your square and D as the point at the bottom, then of course your final answers would swap. Okay. Right. Yeah, so if you really check your final answer and compare it with the diagram that you have, it makes sense to have -5/2 and -3/2 here as your complex number represented by B, because B is a point in the third quadrant where both the xy coefficients, both the xy coordinates are negative. And so it makes sense for B to be at the third quadrant. And D is having a negative x coordinate and a positive y coordinate. So it makes sense for D to be in quadrant 2. And according to your diagram, D is indeed in quadrant 2. Okay, so our answer makes sense here. Right, so that's all for this video. I'll continue with page 20 in the next video.